In this experiment, a patterned 8-inch semiconductor wafer was used as the reference surface. A baseline image was first captured under fixed illumination, fixed camera geometry, and controlled acquisition settings. 2 separate human hair specimens were then placed onto the wafer surface, and a second image was acquired under identical conditions. The region shown in this demonstration is only a small crop measuring 250 by 200 pixels, extracted from a much larger patterned wafer image. Despite the limited field of view, the crop contains 2 foreign material disturbances embedded within a complex semiconductor-style background. A typical human hair is approximately 60 to 100 microns in diameter. By comparison, many of the visible wafer structures in this image are substantially larger, creating a challenging inspection environment composed of repeating patterns, boundaries, and reflectance variations. At first glance, this may appear to be a simple contamination detection exercise. However, the objective of this experiment is different. Rather than asking whether a hair is present, the system evaluates how the physical state of the wafer has changed relative to a defined reference condition. Using the PASDE, physics-anchored Semantic Drift Engine, measurement framework, the reference image and detect image are compared to generate a physics-anchored drift field. This drift field quantifies localized changes in optical response caused by the presence of the foreign material. The resulting heat map reveals multiple disturbance regions associated with the 2 hair specimens. Rather than identifying the hairs as objects, the system identifies regions where the measured state diverges from the reference condition. The directional arrow overlays represent portions of the directional instability field generated from the measured drift response. These arrows illustrate the orientation and magnitude of localized disturbance behavior within the inspection domain. An interesting observation is that the measured disturbance field extends beyond the physical diameter of the hair itself. The system is not simply responding to the foreign material, but to the broader optical disturbance created within the inspection environment. Scattering effects, shadowing, reflectance changes, and local interactions with the wafer pattern contribute to a measurable directional response surrounding the contamination. The experiment also demonstrates the ability to identify multiple disturbance sites within a single inspection region. Separate portions of each hair specimen generate localized directional responses, producing multiple flagged regions rather than a single binary detection result. This distinction is central to the Phocoustic approach. The objective is not merely to classify a contaminant. The objective is to measure physical change, quantify state deviation, and evaluate whether the inspected surface remains in conformance with its intended condition. In this demonstration, 2 hair-scale foreign material disturbances generated measurable directional structures on a patterned semiconductor wafer, illustrating how reference-anchored measurement can transform subtle physical changes into quantifiable inspection artifacts. For Phocoustic, the question is not simply, is there contamination? The question is, how has the physical state changed, and can that change be measured?